This is our continuing series of lectures on fundamentals of transport processes. Through the course, initially we had derived conservation equations for mass, heat and momentum transfer. In different coordinate systems, I had derived it explicitly for you in a spherical coordinate system as well as a Cartesian coordinate system. The equations have a common form. They all are of the form u dot grad T plus partial T by partial T is equal to the thermal diffusivity times del square T plus any source. Okay. And so, on the left side is the convection terms, the time derivative, the rate of change of temperature and the rate of transport of temperature due to the mean fluid velocity. On the right side is the rate of transport due to diffusion, molecular diffusion, and then any sources or sinks. We had scaled, if you recall, in the previous one of the previous lectures, T star is equal to T minus T infinity by T naught minus T infinity. Here T infinity is typically a temperature that is far from the object, and T naught is the temperature at a surface. And we had scaled the velocity, u star is equal to u divided by the characteristic velocity, the average velocity in a pipe or the free stream velocity for the flow around a particle. Okay. And we had also scaled the length. Okay, by a characteristic length, the pipe diameter, the particle diameter and so on. And consequently, the gradients all got scaled. Okay. Here this first one is the gradient of the temperature, the second one is the Laplacian, okay, and I had explained to you what those things mean. And if you do that, okay, you also have to scale time. The only time scale that is available to you is u by L, okay, either u by L or alpha by L square. In this case, we will scale it by the convective time. Okay. And then I had shown you that the temperature field, the equation reduces to this multiplied by a Peclet number is equal to del square T star, okay, if we have no sources or sinks. Okay. And this, the Peclet number is equal to u L by alpha. It gives you the ratio of convection and diffusion in this system. Last few lectures we have looked at the case where diffusion is dominant, when the Peclet number is small for heat or mass transfer, in which case we can neglect the convective terms altogether, and the equation just reduces to an equation for diffusion, a Laplace equation or a Poisson equation for the temperature or the concentration fields. And I had shown you how to get solutions of those equations. Typically you would get a solution either by separation of variables, okay, in which you separate the variables in the three directions, or you can get it by assuming delta function sources and then integrating them out. Okay. And I had shown you that those two are actually equivalent to each other in the last lecture. In this case, we are going to consider the limit for the next few lectures when this Peclet number is much larger than 1. That is when convection is large compared to diffusion. Okay. So, our next series of lectures are going to be about high convection dominated transport. Okay. So, let us take the simplest case, okay. Flow past a flat plate, horizontal surface, the stream y's direction is x, the cross stream direction is y. We will assume that there is no variation in the direction perpendicular to the plane of the board, which is the z direction. Okay. At the surface itself, fluid is entering, okay, with velocity T infinity, and at x is equal to 0 starts a heated section, okay, a heated section. Let us for the moment assume that it has a length L. Okay. And this is a flat solid surface, so that for x less than 0 the temperature is T infinity everywhere. The fluid is coming in at T infinity at temperature T infinity, and only for x greater than 0 at the surface y is equal to 0 there is heating of the fluid. Therefore, you would expect that there should be thermal diffusion into the fluid starting at x is equal to 0. Okay. Transfer from the fluid to the transfer from the wall to the fluid. Now, this is an idealization of course, but we will see that correlations for many practical irrelevant flows are actually obtained in this way. The solid is a solid, the surface is a solid surface. Therefore, the velocity profile close to the surface can be approximated as a linear flow. At a solid surface, both components of the velocity have to reduce to 0 from the no slip condition, and therefore, at the surface itself the velocity has to be equal to 0. Near the surface the velocity has to increase linearly from 0, because the shear stress at the surface is non-zero. The fluid is exerting a non-zero shear stress due to viscous diffusion. Therefore, the velocity has to increase linearly. Okay. And I will approximate the velocity in this case close to the surface as ux times gamma dot y. For the present purposes, as we shall see a little later, it does not really matter what the velocity field far from the surface is, because we are considering the limit of convection dominated transport. And in this case, as I had said, we would expect the disturbance to the temperature to be restricted to a thin boundary layer near the surface. So, we would like to calculate what is the temperature field within this region, and from that what is the flux, and therefore, the Nusselt number correlations. Okay. So, we have the boundary conditions are at y is equal to 0, t is equal to t naught. Okay. Since the fluid is entering with a velocity t infinity, okay, the velocity far from the surface has got to be equal to the same as the entering fluid velocity, because you would expect the transport to be confined to a thin region near the surface. Okay. And at the location x is equal to 0, okay, t has to be equal to t infinity for all y, because that is the start of the heating region. Okay. The fluid is being heated only for t greater than for x greater than 0. Okay. We will consider steady state. Okay. The diffusion equation is ux partial t by partial x is equal to alpha partial square and that is because ux is the only non-zero component. Okay. This first term is u dot grad t, okay, which is equal to ux partial t by partial x plus uy that is the term on the left side. Okay. And in that term uy is equal to 0, there is no velocity in the y direction, and there is no transport in the z direction. So, you just get ux times partial t by partial x. Okay. And on the right side, okay, in general the expression would be del square t. Okay. It would be of the form plus d square t by dz square. But since we have assumed there is no variation in the direction perpendicular to the surface, this term can be neglected. Okay. And throughout we are going to consider the limit of high Peclet number. I will come a little later and define exactly what that is, that Peclet number. Okay. So, then we scale coordinates. Okay. The natural scaling for temperature T is equal to T minus T infinity by T naught minus T infinity, the scaling that we have always used. Okay. the length scales, okay, and ux star. Okay. Okay. In this particular case, we only have the strain rate at the wall. Okay. We only have the strain rate to the wall. Therefore, I have to scale ux by gamma dot L. Okay. That is the only length scale that I can get, okay, for ux. Okay. Insert that into the conservation equations. Okay. So, I will get gamma dot L by L, okay, partial T star by partial x star is equal to alpha by L square. Since I have two derivatives in the Laplacian, I will get partial square T star and scaling I will get gamma dot L square by alpha. Okay, so, that is the equation, and when I scale y here, okay, this y is equal to 0 becomes y star is equal to 0, t star equals 1, y star goes to infinity. When y goes to infinity, y star also goes to infinity, it is y by L. You can see that T star has to be equal to 0. You have to recover the undisturbed temperature field. Okay. And similarly, at x star is equal to 0, T star is also equal to 0, okay, for all y. T is equal to T infinity corresponds to T star is equal to 0 from the scaling, and T is equal to T naught corresponds to T star is equal to 1. Now, this is the Peclet number for this problem. Okay. In the limit of high Peclet number, okay, okay, for high Peclet number, you would think you can neglect the right side of the equation and just get an equation of the form partial T star by partial x star is equal to 0. Okay. This just tells you temperature is independent of the x coordinate. It just tells you that temperature is independent of the x coordinate. What that means is that the temperature is a constant. It is equal to the temperature at of the entering fluid, because this is the entering fluid that is going along, okay, downstream. So, the temperature is independent of the x coordinate. The temperature is the same everywhere, and there is no way to satisfy this boundary condition that T star is equal to 1 at y is equal to 0, because at the entrance T star was 0. Therefore, as it goes along the fluid velocity streamlines, the temperature has to be the same. Okay. In fact, in the high Peclet number limit, the equation just reduces to u dot grad T star is equal to 0. If I neglect the diffusion terms, okay, it just reduces to u dot grad T star is equal to 0. Grad T star is the variation in T star in along a particular direction. U dot grad T star is the variation in T star along the velocity direction, okay, along the direction of the velocity. Therefore, if u dot grad T is equal to 0, that means that there is no variation of the temperature along the fluid streamlines. Therefore, the temperature is a constant along the fluid streamlines. In this case, there is no way we can satisfy the boundary condition at y is equal to 0. Physical reason for that, we have neglected the highest, the mathematical reason is because we have neglected the highest derivatives in the conservation equation. And when you neglect the highest derivatives, you cannot satisfy boundary conditions anymore. The physical reason is that we have neglected thermal diffusion. Transport perpendicular to the surface can take place only by diffusion, because there is no convection perpendicular to the surface. Therefore, this transport perpendicular to the surface has to take place only by thermal diffusion. And since when we neglected diffusion in the high Peclet number limit, we have effectively neglected transport perpendicular to the surface, and therefore, in the approximation that we have made, there is no transport perpendicular to the surface and there is no way to heat the fluid, because it is only transport perpendicular to the surface that can heat up the fluid. The fluid flow is only parallel to the surface. In the real system, of course, close to the surface there is going to be transport. We are in the limit of high Peclet number, where the downstream convection of the fluid is much faster than the cross stream diffusion. Okay. We are in the limit of high Peclet number, where the downstream convection is much faster than the cross stream diffusion. Even in that case, there will be diffusion, but it will be restricted to a thin region near the surface, because whatever is coming out of the surface is getting swept away downstream very fast due to the fast flow. Because of this, the temperature disturbance will be confined to a thin region near the surface. Therefore, we have to scale the cross stream dimension differently in compared to the streamwise direction. We have to scale it by a thickness of the region where the temperature, where the heat has diffused. The thickness of that region will decrease to 0 as the Peclet number becomes larger and larger and goes to infinity. The thickness will be smaller as the Peclet number is larger. However, when you have scaled the equations by the correct thickness, the equation itself will be independent of Peclet number in the limit as Peclet number goes to infinity, so that in the scaled equations there is still a balance between convection and diffusion even in the limit as the Peclet number becomes larger and larger. The convection to diffusion becomes larger, the thickness becomes smaller. If you have scaled the equation by the correct thickness, the equation itself will be independent of Peclet number in the limit as the Peclet number goes to infinity. So, that is the idea. So, let us do the scaling once again. Okay. So, this is the problem. And the boundary conditions. Let me just write it in dimensional form for the present. I will just tell you why I am doing that. At the surface itself, T star has to be 1, I am sorry, okay. And then at x is equal to 0, okay, T star is equal to 0 for all y. My conservation equation. Now, I will scale x by L, of course, because the streamwise extent of the surface is of course the natural length scale for this. Okay, the streamwise length of the surface is the natural length scale, but in the cross stream direction I should scale y by what is called a boundary layer thickness delta, okay, a boundary layer thickness delta. Okay. And if I do that, the equation becomes gamma dot delta y star by L where I have scaled y by delta and x by L. In the diffusion term on the right side, the largest term is this one, because 1 by delta square is much larger than 1 by L square. Delta is much smaller than L. So, I would expect 1 by delta square to be much larger than 1 by L square. Okay. Therefore, the right hand side can be written as alpha by delta square I am sorry. Okay. So, now what I can do, this term is small compared to the first term. This means that the streamwise diffusion is much smaller than the cross stream diffusion. The cross stream diffusion is what is transporting energy from the surface. The streamwise diffusion takes place over a characteristic length L, whereas the cross stream diffusion takes place over much smaller length delta. Okay. And because of that, streamwise diffusion can be neglected in comparison to cross stream diffusion in the high Peclet number limit. In other words, there is a balance between the streamwise convection and the cross stream diffusion. Okay. So, now I can scale the equation. Okay. I can divide throughout by alpha by delta square. Okay. And what I will get is that gamma dot delta cubed by L alpha y star partial t by partial y star is equal, I am sorry, x. On the left side you have streamwise convection, should be x okay. So, that is the balance equation. And now this thing, okay, for a balance between convection and diffusion, even in the limit as the Peclet number becomes larger and larger, you require that this term is finite. Okay. The term in the red box has to be finite even in the limit as the Peclet number becomes larger and larger. So, that within the governing equation itself, convection and diffusion continue to be of equal magnitude as the Peclet number becomes larger and larger. Okay. So, that is the idea. What this means is that gamma dot delta cubed by L alpha is equal to 1. Okay. Alternatively, delta by L whole cubed is equal to alpha by gamma dot L square. Okay. And this, as we just saw, was the Peclet number inverse. Okay. If you recall in the previous slide, we had defined the Peclet number as gamma dot L square by alpha. Gamma dot is the strain rate at the surface. It has dimensions of 1 over time because it is the slope of the velocity, okay, the derivative of the velocity with respect to y. Okay. So, it has dimensions of 1 over time, length is length square, and alpha is of course the diffusivity, which is length square per unit time. Okay. So, that is the Peclet number in this case, and this implies that delta by L is equal to the Peclet number power minus 1 by 3. Okay. So, that is the boundary layer thickness. The thickness of the boundary layer in the limit of high Peclet number has to go as Peclet number to the minus 1/3 power. Okay. So, this is just a scaling argument. It has told us that the temperature has to reach, okay, T infinity, okay, within a region of thickness Peclet number to the minus 1/3, okay, times L. That is the thickness of the boundary layer if the length of the plate is of length L. It has not yet given us a solution for the problem. You can get a solution using a similarity transform technique, okay, and the justification, the physical justification is as follows. Okay. At any given location x, okay, at any given location x, okay, we are making a balance between streamwise convection and cross stream diffusion. Okay. Streamwise convection is going from left to right, okay, and cross stream diffusion is in the cross stream direction. In the limit of high Peclet number, we can neglect streamwise diffusion in comparison to cross stream diffusion. Okay. And therefore, in this limit, the temperature at a location x should not depend upon the total length L, because the total length of that plate is downstream of the location x. That cannot affect the flow upstream, because we have neglected cross stream streamwise diffusion, and convection is downstream. Therefore, the temperature at a location x cannot depend upon the total length, it has to depend only upon the distance x alone. Okay. In other words, for the temperature field at a given location x, the only relevant length scale is x itself rather than L. Okay. Therefore, the boundary layer thickness at a given location x has to be defined only in terms of the distance x from the start of the heating section. Okay. So, L is no longer a relevant parameter. Okay. The only relevant parameter is x itself. Okay. The original equation that I had, once again, okay, gamma dot y partial t by partial x is equal to alpha partial square t by partial y square, okay, where I have neglected, okay, streamwise streamwise diffusion in comparison to cross stream diffusion. I had made a balance between cross stream diffusion and streamwise convection. If the temperature at a location x depends only upon x itself, that means that I should be able to write a similarity variable as y divided by a thickness that depends only upon x. It could well depend upon gamma dot and alpha as well, but it depends only upon the streamwise distance. This will be my similarity variable. Okay. And if I write the equation in terms of the similarity variable, if I have done everything correctly, right, this equation itself will tell me, give me what is the form of this delta of x, okay, for a similarity solution to be valid. Okay. So, how do we do that? Okay. Now, both the temperature function of x and as a function of y, I need to express in terms of this function eta. Okay. So, partial t star by partial x minus y by delta square d delta by dx. Okay. Just differentiating this by chain rule with respect to x. Okay. And I can write y by delta as once again as eta. So, I will get partial t star by partial eta into minus eta by delta d delta by dx. Okay. And the derivative with respect to y is quite easy. The second derivative okay. And now I have to collect terms on the left and the right sides. Okay. So, let us do that. Okay. Gamma dot into y is delta times eta. Okay. Partial t star by partial x is minus eta by delta d delta by dx, okay, into dt star by d eta is equal to, on the right side I have alpha divided by delta square. Okay, so, that is the differential equation that I get, and I can multiply both sides by delta square by alpha, okay, and collect terms. What I will get is gamma dot delta square, okay, d delta by dx, okay, and there is a 1 over alpha, okay, into minus eta square So, this is the equation in terms of the similarity variable, and for a solution to exist for this equation, as you can see, this term here has to be equal to a constant. It should not depend upon x or eta, it should be equal to a constant. If this is a constant, then the rest of the equation is only a function of eta, and therefore, I can get a similarity variable for the problem in terms of the temperature field for eta. Okay. How do we get the similarity variable? So, the solution in terms of the similarity variable, and how do we use that to get correlations for the heat transfer coefficient? I will continue this in the next lecture. I will see you then.